Okay, just to remind you where we ended things. Our simplest type of strongly interacting theory is a theory with one running coupling. So coupling is in scales, the normalization group scale. But if you change the normalization group scale, you can compensate by changing the coupling, hence the notion of running coupling. Theories like this, if you didn't know about running and the normalization group scale, looked like the theory is dimensionless. The couplings of the theory are dimensionless, and naively you would have said that there was no scale that would come in a physical quantity. Okay? There are no masses that you could have in this theory because the theory is defined only in terms of dimensionless numbers. But because of the normalization group scale, there is the sneaky scale lambda QCD, which can be a function of a running coupling and mu. And even though mu is arbitrary, you can still have a solution to this equation. If you've never tried to solve it, try. Just knowing this much, you can find that there's a unique solution up to a proportionality constant in terms of the beta function. Suppose I give you the beta function. There's a unique solution to this equation up to an overall constant that says that even though mu is arbitrary, there is a fixed scale which could be a physical scale, and all the masses and dimensional properties of the theory would be proportional to that scale. And so that's our lambda QCD. Now we ended up yesterday looking at a theory that had this kind of property, that instead of asymptoting to weak coupling, it asymptoted to some other coupling of so hence a kind of a fixed point of the renormalization group, alpha star. And alpha critical may be the scale, the coupling which triggers the formation of bound states. So this is where we were, and since I can continue this picture more, you can see that if you want some tool to try and study what physics of this type is like, it would be nice to start with a kind of cruder approximation, which is just to look at this region here, where it looks like the beta function, it looks like the coupling is hardly changing at all. So an approximation to that is beta of alpha, so this particular value of alpha star equals 0, okay? The so-called fixed point of the beta function is when it stops altogether. Okay? And so we would like to know what this world is like. And I said I'd at least like to show you in what way in this story of what it might be like, how you could try to even imagine one example of what life is like in a world like this. How you can engineer or construct plausible scenarios of what this physics is like for yourself, so that one can play with it and use it as the first approximation to a world which looks more like this, where ultimately something interesting happens in the infrared, but the departure point is this. Okay, so we want to understand how you do that. And so I'm more or less sketching. Again, I'm really trying to point you towards my paper on ADS-CFT. I'm trying to rework it in the manner that non-string theorists would find useful. So you can read all about it there. And that is a more technical paper, taking you hopefully step by step through one way to arrive at this famous result of ADS-CFT. Okay. But let's start by just trying to figure out what life is like here. In a world like this, there is no intrinsic mass scale. You see, the key, that's why I wrote this down, maybe you've all seen this before, but the reason I wrote this down is the reason that there is an intrinsic mass scale in QCD is because of the running of the coupling. Okay. Otherwise, without this scale, if this scale was unimportant, as it is here, there's no run. Then what you see is, what you would have thought naively is what you get. This is the theory which has only dimensionless couplings. I'm not even putting any mass parameters. This is like massless QCD. In a theory where there's only dimensionless couplings which specify the theory, then there is no intrinsic mass scale that an experimentalist could say, that's a special mass scale. Okay? That's the size of an atom. So let's see what this world looks like. So in order to do this, I'm going to draw 3 dimensions like this. Okay, so schematically, 3 dimensions are being reduced to 2 dimensions so that I can draw on the blackboard. Now, what could we imagine being in this theory, 3 dimensions? What kind of object could it have? Well, we can try and say maybe it has an atom. Okay. So that's a perfectly good try, given our familiarity with our own world. You might say, I hope it has something as interesting as atoms. But the normal atom of atomic physics has some intrinsic scale to it, whatever it is, the rhythm. I don't know. Whatever it is. It goes like 1 over a fine structure constant times the mass of the electron. So if you have intrinsic mass scales in your theory, you can get intrinsic length scales. But we don't have any intrinsic mass scales. There may be an atom. But it means that if there is this state, then there must be this state as well. There must be a state where I rescale the thing, or shrink it. So these shapes might exist. The atomic shape, the structure of the wave function, or whatever. But I can shrink, I don't know if it's obvious that I'm trying to draw something self-similar here. I can shrink or magnify whatever shape, whatever wave function or wave functional you give me, describing some sort of physics. And that's because a theory which doesn't have an intrinsic scale, not only does it have Poincare invariance, the usual symmetries of quantum field theory, 3 + 1 dimensions, it also has scale invariance in some way under where you rescale all the lengths by an overall constant. Okay. And so this is just saying we've got to have all of these options now. And since we are the home of so many great artists, you see automatically, I'm sure, that there is the optical illusion that you can take it, there's a standard illusion that we are used to, which is either you try to draw things on a flat piece of paper which looks small or big, or you can imagine that the object you're looking at is a fixed size, but it's closer to you or it's closer to you or further away from you in some fictitious direction. Okay. So I've used x, y, z. Let me introduce a fictitious coordinate w that does this. Okay. So this is the root of the geometrization that I was referring to the last few days, that whatever quantum wave functional that describes some aspect, some state that can be made out of a weird theory like this, we can shrink it or magnify it, but then we can always choose as our language to switch. We're unhappy with the loss of intrinsic scales that we just say, I insist that there is an intrinsic scale to physics, and that this is merely an optical illusion. Things that look small are really just further away, and they have fixed size. Okay, so that's the trade that we're making. Okay, so now there is a problem. This sounds like such a dirty trick that you think something's going to go wrong. For example, if you well, let me go through each of the complaints that you might have. If the, this is the orbit of something,
So this is not just a static state. This is a dynamical picture where the electron is whizzing around and so on. Then something goes wrong because the scale invariance we're talking about, the rescaling, is rescaling all 4 coordinates of space-time. And that means that when I rescale the size, the orbital time for this electron is also getting rescaled. So the period of orbit is getting smaller here and getting bigger here. Okay? So you lost the illusion, because normally, if I take the atom in this thing and I bring it closer to you, the orbital time of the atom, of the electrons in the atom, is exactly the same there as it is there. But that's, of course, a consequence of translation invariance, right? So this cannot be translationally invariant. In fact, this notion that timescales for physical processes can slow down is very easy to accommodate and is in fact a feature of the real world in curved space-time. So this W direction, this illusionary picture is can easily be accounted for by curved space-time. And this shifting of the timescales is a kind of one of the many things called gravitational redshift. In particular, it's something called gravitational time dilation. So it's actually true that you can actually do this. This experiment has been done probably numerous times. If you take a clock and you put it in a balloon, and you take a clock and you put it on Earth, the clock on Earth will tick slower. It's not moving, but the clock on Earth, lower down the gravitational field, will actually tick slower by a fraction 10 to the minus 9 than a clock in a very high altitude balloon. So we can actually do the experiment to be done. This is a tested fact. So if you want to understand why this clock is ticking slower than this clock, just by moving it in the W direction, it's easy. You just have to say that there's a gravitational field where this is down. Okay? In fact, if I say, okay, then I'm going to try and write the metric of the illusionary space-time. Okay? Well, it has to have Poincare invariance and involve the usual 3 plus 1 dimensions. So the metric is the usual AW nu, dx nu, dx nu. If I wasn't thinking, I would write minus dw squared, just like this, and hope that it was just 5-dimensional in cosmic space. But we know it has to be this redshift effect. And that's easy. It goes exactly the proportion, the rescaling goes exactly proportionate to how much you magnify or shrink. And that's easily accommodated by this method. Okay. In fact, when you do the little bit of detector work, this is the unique metric that would be Poincare invariant in the usual 3 plus 1 dimensions, which would have the properties that I just outlined. If you want fixed dimensions, you can put in an overall radius of curvature, because this is nothing but the metric of 4 plus 1 anti-de Sitter space. And so you can write an overall radius of curvature of anti-de Sitter space, which is a constant radius of curvature. We often work in r equals 1 units for length, but there you go. Okay? So there is a proposal that this is the metric. Now, it seems, again, next complaint. Since this is a dirty rotten trick, it should not really work in any deep sense. We also have to ask, so here, in 3 plus 1 dimensions, let me draw Fontino here. Okay? But we know that if this really was some sort of 3 plus 1, 4 plus 1 dimensional space, even this space, forget the W first, forget this. Here, it's even, let's say, a flat space. There should be some sort of symmetry, if it's worth calling it a dimension, there should be some symmetry that relates the fake dimension to the true dimensions. There should be some way of rotating W into any of the x mu directions. Okay? Either boosting it with time or rotating it with space. There should be such symmetries. Indeed, even though you put this so-called warp factor into your metric, even though it is not in Minkowski space, there's a generalization of exactly these rotations. You can find them for yourself. But there are exactly such things in this metric. But just to see because in order to give the solidity of 4 plus 1 dimensions, we want to be able to rotate Contino somehow, okay, turn them around, and see that it really is a solid thing, right? So we gotta get this aspect. Now, surely there's nothing here on this board that is telling me that I'm going to have this symmetry. Okay? That's too much to ask. But there's a piece of magic. In other words, I consider this a prophecy. It didn't have to happen, it seems, but amazingly, this symmetry, which we don't even insist on, seems to be.
So it's a very strong conjecture in quantum field theory. All examples subscribe to it. And there's a lot of argument that seems to make it close to a theorem. So take it on faith. That theories of this sort, which are quantum field theories of this sort accidentally have this symmetry. Okay? And of course, this is the geometric version of the symmetry where I've already been talking in terms of the illusion. Even before you go to this illusionary space-time, just like, so these so-called scale invariant quantum field theories also have this symmetry. I'll just do the infinitesimal version of this. Okay. So this is a rather bizarre looking symmetry, and these are called special conformal transformations. And theories, quantum field theories that enjoy this much symmetry automatically have this much symmetry. And if you want an example where you can try and see that for yourself, just consider the dumbest theory which has this, namely massless free field theory. So let me just do action equal to equal x. Okay. You can check that it has, of course it has this one. You can check that it has this. So phi prime of x is equal to phi lambda of x. But then you can't, this will not work. But I think if you put a lambda or a lambda to the plus or minus 1, I forget which, you can check that that is a symmetry of the action, an invariance of the action. Similarly, you can check that for the right prefactor, the right product, the right function of x multiplying phi, that this can be replaced by this. Okay, so this is also a symmetry of this action. But just like the naive, if you go around doing the naive thing, which is just to, you just say, oh, the new field is the old field at the transformed argument, that is not good enough. It's not even good enough if you want to check the scale invariance. You have to put something in here. So you can check that this is also a symmetry. You can put it in the argument, but then you also have to change the field a little bit. So the field transforms and the argument of the field transform. But when you do that, you can check for yourself that this is in fact a invariance of this thing. You didn't ask for it, it's not apparent. The fact that scale invariance is true would have been fairly obvious because there's no mass scales here. So this is just some way of proving that fact to you. But this one you wouldn't have seen coming. Okay? It's something from this other world. Hint that it's relevant. In fact, the set of these infinitesimal transformations, you can make them even finite transformations, fills out the Lie algebra of the group, or the group itself, called SO4, 2, and this is the so-called conformal group. Okay? And that is a symmetry of anti-de Sitter space in exactly, by the way, it's anti-de Sitter space in 5 dimensions, in 4 plus 1 dimensions. This seems to be some weird Lorentz group with 2 times and 4 space dimensions in 6 dimensions.
But you should think of anti-de Sitter space as the analog of a two-sphere. So a two-sphere has a symmetry group which is SO3. Okay, with the two-sphere you can embed it in three-dimensional space and you can view it beautifully there, and it's symmetric under the rotations in SO3. Now this is exactly the analog of a sphere, except with a funny opposite sign of curvature and Lorentzian, and it's embedded in a beautiful symmetric way in six-dimensional Minkowski space of this sort. Okay, so there's some beautiful symmetry structure that underlies these scale invariant theories, and hence we call them conformal field theories. And they can be geometrized in some way, it looks like, into five-dimensional anti-de Sitter space. The piece of magic that has been so exciting for people who are interested in quantum gravity is that this is just a quantum field theory. There's no attempt to put gravity into the theory. But this anti-de Sitter space here actually contains gravity inside. In other words, not only is there an illusion of extra dimensions, there's also an illusion of gravity, but not the usual gravity of 3 + 1 dimensions, but a 4 + 1 dimensional gravity. And you can get a sense for how that happens in the following way. So, surely, there's a way of creating state. You can ask what kind of states are there in this theory. But there is a kind of state that you can create. You can take local operators of my field theory and act on a vacuum, and that'll be a state. Okay. Here's a local operator, the energy momentum tensor of any quantum field theory should have an energy momentum tensor. It turns out that this is a symmetry. Scale invariance is a symmetry. And it turns out that the conserved current for scale invariance, I'll give you the version that you would check formally, and then there's some slight subtleties. But if you know enough about how these delta currents work, then it's not a bad bet. This is the translation generator, and you are a rescaling can be thought of a translation in an x-dependent way. And so this turns out to be the but the conservation of the scale current then tells you that that's nothing but the trace. You already know that this is conserved. So using the fact that this is conserved, the conservation of the scale current is given by the trace of the energy momentum tensor, so that's okay. So we already know this just by translation invariance. So here are two relations. Okay. And that means that out of the naively 10 degrees of freedom in the symmetric, so you can also choose T mu to be symmetric. Out of the 10 symmetric components of T mu nu, 5 of them are killed by these relations. So there's sort of five polarizations. And that's because the typical state that you make like this is a massive state. I didn't say it's a particle, but it's a massive state in three-dimensional space. So the spin-2 nature of what this thing creates spin-2 excitations, and massive spin-2 has 5 polarizations, as we all know. Okay. But that means that this thing creates some little, so a local operator acting in the vacuum creates some little dot. Sorry. Yes, sir.
It's because I'm not used to this, so maybe but the T mu is an object that lives in the anti-de Sitter space, right?
No. T mu is something that lives on the screen. It lives in standard quantum field theory. T mu is just the.
So mu runs, it doesn't run to 5 dimensions, it runs only to 4 dimensions.
Sorry, does this run? Is that the question?
Yes.
You guys talk about the mu index, right?
Yes.
Oh, these indices run from 0, 1, 2, 3. This is the CFT.
Okay.
It's this guy's
Okay.
space.
Okay.
So if you do the counting, you'll find that there are 5 polarizations. But because it's a tensor, so that gives you the 5.
Yeah, okay.
So here it is. I'm still starting my story on the field theory side, not the illusionary side. And so it creates some little dot. And now I give it some time to expand, which is just to take the Schrödinger operator and turn it into a Heisenberg operator, so it includes time evolution. And I let it expand, and it turns into something. Okay. There it is. Now, if you decompose the rotation group of four dimensions down to 3 dimensions, the fact that this is it's still spin 2 in the 4 plus 1 dimensional sense. Whatever this blob of stuff is, it's some state with spin 2. But in 4 plus 1 dimensions, so spin 2 in 4 plus 1 dimensions would imply 9 helicities, or 9 polarizations. It's easy enough to work out for yourself. Just imagine being in 4-dimensional Euclidean space. I'm just talking about space. And in that, so you're just doing non-relativistic quantum mechanics in 4-dimensional space instead of 3-dimensional space. And just take the symmetric traceless combination of 2 spatial vectors, okay? And ask how many components that has. In 3 dimensions, that has 5. In 4 plus 1 dimensions, it has 9. Okay. And so you're expecting that if somebody tells you I have a spin 2 blob in 4 plus 1 dimensions, you should expect that that blob has 9 polarizations. But there's a mismatch, because this blob, because secretly there is no extra dimension and it's all a cheat, it only has 5 polarizations. So there's a mismatch. And so again, you think, okay, crisis, the whole illusion is breaking down, this is all nonsense. But this calculation of 9 polarizations is if the mass of the particle in 5D, the 5-dimensional mass, is non-zero. Otherwise, you can't be an undergrad and do the calculation in the rest frame of the particle. It has to be at rest to count like an undergrad counts. Once again, if you do M5D equals 0, you can again become a relativistic group theorist, go to the little group, blah, 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 and you find that it has to have 5 polarizations. Okay? And that's a perfect match. So even though these 5 polarizations here are massive in the 4-dimensional sense, I just told you there are no intrinsic mass scales. That doesn't mean that there aren't states which have mass, invariant mass. It just means that for any state with an invariant mass, I can make a state with a different invariant mass. There's no intrinsic mass scales, but of course any state has mass. It's just like Maxwell theory, or this theory. It's the theory of free photons. The photon is massless, but if you give me a pair of photons pointing like this, of course the pair of photons will have some invariant mass, right? So there's nothing wrong with having an invariant mass, or mass squared. Okay. But what we're finding is that even that the states created by this, they are massive according to, this is a Casimir, group theory, this is a Casimir of the Poincare group. It can be non-zero. This is a completely different Casimir. It's a Casimir of the conformal group. And what it's saying is that the only way to match up the illusion is if the 5-dimensional mass is 0 for whatever the spin 2 particle is. Okay. So we have M equals 0 and J equals 2 in ADS 5. The universality of energy momentum tensors in quantum field theory translates to the universality of having a massless spin-2 particle, or spin-2 state in ADS-5. Now, a spin-2, normally, what's the difference between a particle and a state? A state can sort of fall apart, you pull it apart into several pieces. A particle, you presumably can't, or it's harder to do, or you have to pay a small coupling to do. This is a massless particle. Any state that is secretly massless, operationally, will better be called a particle. It doesn't just automatically fall apart by itself. You call the Z boson a particle because it has a reasonably long lifetime where it coherently just sticks together. A massless state, it cannot ever suddenly fall apart. Two photons that are exactly like this cannot sort of suddenly do that because energy momentum conservation forces them to always be in the massless state. Okay, so this thing is actually a particle. It's an ADS particle. And from my first lecture, we can repeat in ADS-5, or at least in the approximate small scales compared to our ADS, we could try to repeat the arguments that I gave in the first lecture, which says that the only version of this theory that makes sense, if you're trying to figure out what kind of crazy world is this, is one with 5-dimensional general relativity. Okay, so this is why it is so exciting. Somehow, the CFT should be viewed as the DNA of a new animal, and the animal is ADS. Okay. Just as the quarks and gluons of QCD are the DNA of a new animal that emerges in a very complicated way from it, namely the hadronic world. Here, this extra-dimensional world seems to be coming out of this. But that doesn't mean that the physics in the extra-dimensional world is in any way simple, which is what we always like. It doesn't mean that it's a weakly coupled theory. It just means that it has this intrinsic geometric structure, quantum geometric structure, and there's no avoiding that. But we'd like to know under what circumstances it's at all simple. Okay. So let me just say one more thing about that, which is when you have, so just like I use this, let me take a generic operator, act on the vacuum, and create some little dot. And then I watch the dot as time evolves and just, whatever state it is, so the point light spreads, I watch it spread in some way. And we can ask, how can I get the mass spectrum? One thing I'd like to understand is, what is the mass spectrum in 5D? If I want to be a good effective field theorist, here I have my J equals 2, M equals 0 graviton, that's good. But I don't want a lot of other complications. I don't want an infinite number of particles. I'd like to have a handful of particles, hopefully weakly coupled, and then I can try to write effective field theories that describe it. So knowing the mass spectrum, or something about the mass spectrum, is important. So I'll just say this much, that when you have these operators that create a state, and here we're looking at this state, one way to measure the mass is to look at the mediation of Yukawa forces. Okay. So one place that masses appear is if you try to use the particle whose mass you're questioning, you try to use it in some Yukawa, you try to use it to mediate a force. And if it's a massive particle, then you'll have a Yukawa suppression of the force, and if it's massless, you won't. So we'd like to see, do we see this kind of Yukawa suppression? And the trick is to use it in the W direction. We already know that all directions are symmetric, because this is a symmetric enough space. So without loss of generality, I'm going to use the W direction to do this. But the W direction, because of the W down here, the physical length is not W, it's log W. So if you want, we're looking for W to the M time, we're trying to look for this exponent m. But in fact, we know that sort of what we're talking about in translating, moving, so I'll just give you the root of the information. When we are translating in the w direction, we are secretly just rescaling physics. So in order to pick out this exponent from the field theory side, the calculation comes down to asking how the state reacts to rescaling, to doing a rescaling. Okay. And this W, remember, is literally the rescaling factor. That's what it is. That rescaling factor turns out to be precisely what we mean by the renormalization group behavior of this operator. That is, how does the operator run? Or if you want, if you put this operator into Lagrangian and you ask how does the coupling run, you can ask how does the operator run? And that would be a scaling dimension. So this thing in conformal field theory will turn out to be something like the rescaling and some exponent, or sorry, some scaling dimension that shows up here. So the duality, the equivalence of these two ways of talking, is that other than some subtlety about being an ADS as opposed to flat space, which I won't bother to waste time on, the higher dimensional mass spectrum is given by this dimensionless numbers, which are the scale dimensions, the spectrum of scaling dimensions that I talked about yesterday in question time. They are one-to-one correspondence. Of course, this is a mass parameter, this is dimensionless, and the units are made up, if you're more careful, by R ADS. Okay, so now this is dimensionless. Sorry. This is dimensionless, and this is dimensionless. And so that's exactly what I was saying in question time, that if you want this to be a nice theory, meaning at least at some sort of low energies as seen by somebody in a small patch of ADS, if you'd like that to be a theory that has effective field theory rules, where there's a finite number of particles and so on, it has that you want this gap. Which means you need a gap. You need a gap in the mass spectrum, and that translates into a gap in the spectrum of scaling dimensions. This is the thing that sets you off. Okay. Now there's some fine details, things like the large end expansion and so on, that I alluded to in question time yesterday. But that's it. That's all I'm giving you, just to push off in that direction. But this is at least to make it plausible that there is a useful geometrization. Once you have heavy particles and integrate them out in your mind, and you try to write the effective field theory here based on the symmetries like general coordinate invariance and all of that, you can find a predictive effective field theory that can be used. Okay? So suddenly you're in business again. From total, where do I start? Okay. But it requires you to make a dynamical assumption, which is, or to have such great control of some particular conformal field theory, like the n equals 4 Suzy angles of infinite fame. Okay. But you have to hypothesize that you do have this gap in the spectrum of dimensions, so that you can have effective field theory that works in a large region. Let me just say, what should we do about this aspect? That the coupling actually isn't exactly like this, that it's actually, at some point, it just rapidly, so in some regime, it just rapidly ends. That rescaling mu cannot be done arbitrarily low, it somehow ends. Which in this illusion would say that you cannot make W arbitrarily big, somehow it should end. Okay, in some messy way, but it should end. Similarly, in the real world, in the ultraviolet, as you keep going, this idea that I can just look, even if there was only the strong interactions to replace the standard model, I can just look at that, I don't have to worry about anything else. Well, one thing that you eventually have to worry about is you hit the Planck scale. The real Planck scale, of real gravity, not this illusionary gravity. And at the Planck scale, gravity becomes strong, and there's no sense in which this field theory lives in isolation. So in some sense, you should hit another wall here. You cannot just keep rescaling things to arbitrarily small distances, because ultimately, you'll be trying to shrink this to be smaller than the Planck length. And as we discussed again in the first lecture, that does not work. Okay? So there should somehow be this W direction, instead of being this sort of semi-infinite thing that goes on forever, it should have some sort of a cut at very small and very large W. And that's exactly in the perhaps dumbest possible, and yet still therefore useful for your imagination way. That's exactly what RS is attempting to do. So this is W equals 0. This is W equals some small epsilon. And this is some W, so this is what I'll call WUV and WIR. And in this picture, you live between, in this interval. Okay, so you can move in 4 dimensions, but in the 5th dimension, you're stuck in this interval. And this is sort of this cavity or waveguide that lives between this wall and this wall. That is the RS space-time background, whatever. And so this is the place where you try to embed the rest of particle physics. This was just meant to be the would-be Higgs sector, strongly coupled Higgs sector, etc., etc. But everything else in particle physics, including the real-world graviton, the real-world electron, etc., has to play out somewhere in this cavity or waveguide situation. We can add them. See, if something is not part of this strongly coupled theory, like suppose this is the strongly interacting sector, and I take some lepton and I put it here in 3+1 dimensions. It does not have any magnification, this, that, the other that happens to it. You cannot suddenly zoom it in and zoom it out. So it's somehow stuck. It's stuck on my board. It does not apparently come out of it. So that, in the illusionary theory, you have to treat it as something, a degree of freedom. You know, if we talk to, again, the condensed matter physicists, they have some degrees of freedom that move in 3 dimensions. They have other degrees of freedom that are stuck on a surface. The leptons are something that are sort of intrinsically stuck on a surface of this waveguide. And then the strongly interacting hadrons are those that are moving in the waveguide. In fact, in a waveguide, you can always do a mode decomposition into the modes that transform under the symmetry group of the long directions, but you sort of Fourier transform away all the different motions in the sideways directions. In extra-dimensional theory, these are called Kaluza-Klein modes. And now that you have a mass gap given by WIR, or given by the fact that you're trying to model the end of conformality in the infrared, you do in fact have hadrons. You suddenly have mass scale for hadrons. These Kaluza-Klein modes correspond to a class of these hadrons. Okay, so anyway, these are the pieces of this duality, and the place to see how it fits into the basic ideas that we've been talking about during lectures is, I think this is a finite set. They're all TASI lectures by me. There's some aspect of this question of light Higgs versus heavy Higgs that I just didn't have time to do justice to. But especially that aspect is covered in the lectures by Contino. And then also take a look at, so in addition to this, which is purely about AES CFT as opposed to RS in any way, this will give you a better idea of the notion of composite Higgs, the brand name composite Higgs, which allows you to understand why the Higgs can be light, whose mass can be comparable to the W boson mass, rather than vastly heavier, narrow rather than very broad. This gives you more of a sense of, at least a quick sense, of the holographic back and forth dictionary in RS as opposed to ADS. And this will also give you some fleshing out of the way that this sort of composite Higgs works in the RS setting. Okay, so that's that.
I'm sorry?
Yes?
Can you just repeat, how do you interpret the Close-Apply modes as handles?
Yeah, so they are, so remember, the things that live in the 5 dimensions are some sort of excitations of the strongly coupled theory. Okay? Now, as soon as you put this boundary here, and you say that W cannot go beyond some value, and you do. So, Kaluza-Klein modes are merely a Fourier transform of all the possible modes that live in the 5 dimensions. The modes that move in 5 dimensions, we've argued by this construction, are the things made out of the strongly coupled theory. Okay. Once I put this in, there's a kind of a gap, which is what we call the Kaluza-Klein mass gap. Okay? But the objects that are in 5 dimensions are nothing but the things made out of 4 dimensions. They're color singlets, because the objects that I was pointing to, I drew the word atom. I could have said the word hadron when I started my story, and just said, hadrons, the proton has a typical size in the real world. But in a world without a scale, you give me one hadron, one proton, I can rescale it to make a big proton or a small proton, and I could repeat this. So ultimately, the objects that I've been talking about are the hadrons of that theory. And any mode that comes out is secretly a hadron. Okay, so I wanted to switch to the hierarchy problem again. And assume that there's some beautiful story of the type that we've just been talking about that's been going on. One question is, there are going to be a lot of hadrons. Okay, let's call them techni-hadrons because we are don't say that outside these walls. There are some hadrons of the theory. And the mass scale, and there's some mass scale for these things. And we haven't seen anything yet. We haven't seen any. This is a very rich spectrum. They carry electroweak quantum numbers. They may carry carry colored quantum numbers. Where are they? Nothing. Okay. So we have to ask a question. Somewhere down here is the Higgs in the spectrum. Somewhere down here is the Higgs boson, and then there's the W. Is it reasonable to entertain this whole picture and to think that the reason we haven't seen this, the only obvious reason is that it's very heavy. It's sufficiently heavy that we at least haven't seen it. Okay. Maybe they're sitting in 2 TeV, and we are going to see them tomorrow, but then we've done all of these virtual tests, the precision tests, and we still haven't seen them. So where should we imagine this to be? We're willing to believe this is the world, but is it plausible that this structure, the weak scale, could be much lighter than this? And so we want to do an exercise to even understand what's at stake. Okay? So first, I'm not going to talk about the real world. I want to do the simplest example, which, however, in an analogous fashion, is provided by the real world, which is how light a hadron can be. Okay? Compared to the going rate scale. So there's some generic hadronic scale, protons, delta resonance, blah, blah, rho resonance. How light can a hadron be? Remember the principle, innocent till proven guilty. So let's take the best case story of a light hadron. The best case story in the real world of a light hadron are pions. Okay? If QCD was just by itself and there were no quark masses, then these would be Goldstone bosons. So then it's really nice because they are about as massless as can be. There's some scale where everybody else lives, but they're exactly massless. So I'm starting with the most optimistic possible picture. But now I say, no, I know, just like in the real world, I know that, so I'm going to use this not as, it's crucial, I'm making many analogies in this. These I have been talking about as eaten by the W bosons. I'm no longer trying to use them as an analog of something eaten by W bosons. I'm now trying to use them as analogs of this object. Because in this picture, we have been trying to say that maybe the Higgs is a composite of some sort. And the puzzle is, if it's a composite, that's the source of the beautiful stories I've been telling you. Where the hell are the other composites? Why is there this big separation? So now we are using this as an analog of a Higgs. Okay. Now, the detailed version of how you realize a Higgs as some sort of Goldstone boson, that's what's called brand name composite Higgs. Read the Contino lectures and references. Okay. But we want to study how well this could possibly be separated. But one thing we know about the real world Higgs is it has couplings, like, for example, it is part of a multiplet that is gauged by electroweak interactions. Okay. So the W boson can talk to it, etc., etc. So unlike this idealized world I just gave you, where there are massless Goldstone bosons, it's a little closer to the real world, where there are order 1 couplings to things outside the strong dynamics. Okay. So I want to couple with order 1, which does not mean strong, it's still weak couplings, to outside the strong sector. Okay, because that is certainly the case for this. And that the impact, the radiative corrections from outside the strong sector may in fact change whatever you think you want, which is a light Higgs and a heavy everybody else. It might change that and force us to think more realistically. Now, in fact, in the real world, we have a beautiful example of that, because electromagnetism couples to these pi plus pi zeros, pi plus pi plus. At some lower rate, even couples to pi zero. Okay. So, this is an order 1 coupling. If you look at alpha equals 137, find that E is equal to 1/3. Okay? So this has got order 1 couplings to this sector. And so we can actually ask, and now we can use experimental data to ask, how big is the gap between the pions, even though they interact with order 1 couplings that screw up their Goldstone status, that violate the Goldstone status. How much of a perturbation is that? But there's a second problem. In the real world, there are what are called current quark masses. Okay? The quark masses are also non-zero, and they also screw up this Goldstone status. So we need to sort of disentangle. If we want to use the real world as an analog computer, we need to disentangle these effects. That's easily done. I won't go through the chiral perturbation theory, but basically, if you take the difference between charged and neutral, that removes the other sources of correction between the other sources of breaking Goldstone status, and this purely focuses on the effect of electromagnetism. So in the idealized world, you can just think of this. If it's just electromagnetism and massless QCD, this would be the pion mass. And in the real world, to subtract out the dirty fact that there is other issues at stake, we calculate this. Okay? So you can calculate this, but how should we think about it? Because from a low energy point of view, if I'm at much lower energies than this hadronic scale, and once upon a time that was the case, you would draw the following diagram for the self-energy of the pion to see what the mass is. Here is the beautiful, pristine goldstone pion being massless. And then you would draw the photon like this. And this is the classic kind of diagram that gives you the quadratic divergence. It would go like alpha electromagnetism over 4 pi. Okay, typical loop factor for doing this. And then, as you did this thing, and you're looking for delta m pi squared, you find that there was some sort of a cutoff dependence. If you just do it without any regulator, you'd say, it's this. Okay, and many of you know this is already the root of what you would call quadratic divergence, fine-tuning problem, blah, blah, blah. And sometimes that's a little philosophically hairy, because it's like, wait, in normalized perturbation theory, shouldn't I get rid of the divergences, and then what is the significance of this kind of calculation? The beauty of the example I'm doing now is none of that is there. Okay? This picture clearly doesn't make sense when the photon. So what we're doing here is we're integrating over photon momentum, right? We're integrating over photon momentum. And this cutoff is a cutoff on photon momentum. But indeed, you would say, look, and I don't want all this, I should just integrate over everything. Okay, I don't want to play all these dirty games, because I don't trust the theorists who have given me the hierarchy problem that they got it right. You should not trust us. One of us is up the back trying to rethink what he got wrong all these wasted years thinking about that. So we got to work through it again. You have to work through it again yourself. But in this example, we work through it again because we say, look, when the photon becomes so short wavelength, the virtual photon is such a short wavelength, eventually it does not see the pion as this point particle that I'm drawing here. Instead, at some point, the photon is going to have to say it's an up and down quark like this, and the typical diagram is and there's lots of gluons here holding it all together. This is the real picture. Okay. And at sufficiently short wavelengths, there is no pion, there is no scalar. There is no quadratic divergence associated with scalar particles or anything like that. There's chiral symmetries for fermions. There are no quadratic divergences in massless QCD. At short distances, asymptotic freedom reigns. You can just work it out. It's just like QED. QED, you will never see a quadratic divergence in some perturbative diagram like that. So the transition scale for where the theory switches over to being weakly coupled quarks and gluons, of course, that's what we mean by something of order lambda QCD. Okay. Which, correctly interpreted here, I mean the GeV scale. So in this example, there really is, it's not some field theorist cutoff, some intermediate step in a calculation. The gods do not know about this cutoff, and it goes away. Rather, there really is this, in fact, what it really means is it's the scale of compositeness of the pion that comes in. When the photon starts to probe the composite, when it now realizes, hey, this is not an elementary particle, boom, that's when the calculation comes to an end. Okay, so fine, the result of doing this is, if you plug GeV in here and you do this, and you compare it to this, you actually do better than you should. It actually agrees better than even saying more than 1. It's not even a factor of 2 off. And there are more refined versions of this calculation, which you can do. There's a nice account of this. This is in some sense a success of QCD when you do it right. I'm being sloppy here. But there's a nice account of it in the book by Pokorski, which is based introducing the notion of QCD sum rules and and it's a very beautiful story where you can see how the quark picture and the hadron picture are sort of complementary to each other, and yet you can really see a numerical calculation come out that you can do yourself. So you should do it. Okay, so you can see how it goes. That the rough picture for compositeness is, do field theory, thinking of the light composite particle as just a regular elementary particle, but then interpret the quadratic divergences as being replaced by the composite scale where all the other, when a photon hits a pion with energies of order of the compositeness scale, the definition of the compositeness scale is it's the scale which, when you hit the pion that hard, the pion breaks apart and you start to spray out other hadrons. So you hit the photon hits the pion, and out comes a rho meson in the pion. Okay. So you can see operationally, that means that the compositeness scale that I'm talking about at least has to be of order the mass of all the other hadrons in the theory. Okay. And that's indeed, that's exactly what, that's why I use G. So we should interpret it exactly like that. That means that when we come back to the real world, and we try to, again, ask, how light can this guy be compared to all of this stuff? We should be taking the Higgs, and we should be coupling it to all the things that we think lie outside the Higgs sector. We can, for example, put the W boson. Put the top one. And we're again going to get quadratic divergences. For example, this is one of the biggest of such things, and it goes like delta mh squared. It goes like 3 over 2 pi squared y top squared. And then the quadratic divergence I will just interpret as this, where this lambda comp is this lambda comp. So we are now seeing that the going rate, the kick, that all the junk outside the standard model gives you is got a sort of calculable size, because you actually assume the standard model effective field theory is valid below here, because below this scale the Higgs does not know it's a composite. We don't have the energies to resolve its compositeness. And so in this regime I can trust the standard model to point to a calculation like this, but however the cutoff of where I trust it, where the calculation breaks down, is in fact the composite scale. So we have a number of things that look like this. And this gives you a gambler, we're only gamblers, this gives you a gambler's idea of where the compositeness scale should be. Because you're getting a number of kicks from a sector that is not very strongly correlated with the strong sector. It's this other stuff, the weakly coupled stuff, the leptons of the strong dynamics, the photons of the strong dynamics are coming in. There's no particular reason why their couplings are specially chosen, and they are giving these radiative correction kicks to the Higgs boson mass, just like the photon is giving kicks to the pion mass in the ring. And we can use this, and this we know this Topikawa is one. We can use this to say that the true mass of the Higgs boson must be the sum of some sort of things like this, and maybe there's some originals, I don't even know what the word original means, but some original mass squared for the mass of the Higgs. The original mass of the pion, meaning the pure, pristine mass of the pion, is 0. Okay? Doesn't get better than that. But presumably it's something like this, and that as a gambler, since each of the kicks is this big, you would expect that the typical going rate should be greater than or order this delta mh squared. Unless there are fine cancellations between the different kicks for no good reason, then you would expect that the Higgs boson mass that you measure would be of order the size of these kicks or bigger, and that implies
So we can now use the fact that we've measured the Higgs boson mass and say something about this scale. I just plug this formula in here. It's easy to do, and you find that the compositeness scale, you would expect, if there were no fine cancellations, the compositeness scale is more than 500 G. Okay, so that is great. Great and bad. Meaning the moment of truth is here. These hadrons, that scale I'm pointing to there, that's 500 JV. So, this was bad before the LHC turned on, because a lot of the precision tests that I was talking about in the previous lectures are already sensitive to this scale, even before we had the energy to go to this scale. And already they were putting severe bounds on this. Now, if you want to see a quick way of going through many different channels of precision tests and estimating how composite Higgs would contribute virtually in precision tests at low energies, filling out a large number of the different types of experiments that I described in a couple of lectures ago, look at the nice paper by many different people last year, describing, among many other things it discusses, composite Higgs and partial compositeness and virtual bounds on the compositeness scale. So even though it was written last year, in some sense it's the executive summary of things that were worked out even before the LHC turned on. And so already precision tests. So these models can still have a sizable parameter space. But if I'm playing the fair game of saying that I'm not allowing fine cancellations for no good reason, then the bounds were already saying that the compositeness scale should be bigger, at least bigger than about 10 TeV. And of course, the LHC has weighed in, and the LHC is already saying that I don't see any composites of the type that might be here up to about, so the LHC. This is the idea that the idea of no fine cancellations, the philosophy of no fine cancellations is called naturalness. And so, hang on, I'll answer that question in 1 second. And the LHC is putting bounds on some of the things creeping close to 2 TeV. Okay. So this is certainly in accord with the non-finding of the LHC. But then there's this thing of no fine cancellations. There was a question.
Yeah, when you say the composite scale, do you mean the analogy of under ECB or do you mean the analogy of F?
I mean the analogy of, in a sense, more like 4 pi f pi, but therefore let me say it more physically, because I haven't done 4 pi f pi philosophy for you in the lecture. It's the scale of these actual masses of the composites which are not. So where are these composites? Because this is what naturalness says. Okay. Now the discrepancy between by the way, precision test things. There's room for another clever idea somewhere there that might loosen these bounds. Some clever symmetry. There's a lot of the tightest of these bounds, say, comes from CP violation. Maybe there's a new way of embedding CP violation in these theories, then suddenly the bounds go down. In some sense, the most robust of these precision test bounds are, so the most robust, the ones where maybe no clever idea is going to solve it in the next year, are probably more like 3 TeV. Okay, so in fact, you saturate that bound, the LHC will happily see these things with great effort. See these things, and wouldn't have seen them yet. So there's some. If you are a fan of these ideas, then there's some model building that needs to be done to understand thorniest
and the least robust of these bounds, because you can certainly play around with it, and you can see solutions. Again, humans are able to see little solutions to different aspects of these precision test bounds, slight changes of the model. There's some hard core of the model that doesn't seem to want to change, but for all the other issues, it just may be that we'd be too stupid. So somewhere in the multi-TV sector is where the bounds place us, either by LHC or by precision tests. But we're faced with this. And so this multi-TeV fact of nature, of directly looking at experiments, versus our expectations as pure theorists from another universe, right? The discrepancy is called the little hierarchy problem. The only way to make sense of this in the parameter space is, in fact, to choose the parameter so that there is some sort of finer cancellation here. Now, it's not fine cancellation in the sense of fine cancellation at 10 decimal places. But when all is told, I mean, it depends on exactly what scale you choose for the composite scale. This bound, this bound, this bound. But when all is told, we're talking about a kind of, most reasonable people would say, a kind of 1% tuning or fine tuning is required. Okay? And you just say, again, you're gambling with your life, right? So you have to say, either the world just is doing exactly this kind of thing. And just because we were 1% probability that things come out in a way that we don't see anything, okay? Yeah. Or this theory is complete nonsense. Now it's not, maybe mathematically it's not nonsense, but it's not the way the universe works. And this is the crisis, the little hierarchy problem. As I said, this name already existed before the LHC because precision tests were already saying something, as well as earlier direct searches and so on. And it exists in any of the paradigms beyond the standard model that has been worked out well enough that we can actually confront it with data. The supersymmetric theory also has its own version of the little hierarchy problem. There is no, you might say, I'm not working on this junk, I'm going to work on the other. There's no other junk that doesn't have this little hierarchy problem and so forth. We don't know. Is it intellectually that by pure thought we cannot just imagine what's going to happen? Or is there a real flaw in the entire way we've been thinking about all of this, these fine-tunings, etc.? So we are not yet sure. And it requires some new people to come in. But new people are worthless if they are already indoctrinated by previous philosophy. So you have to be aware of what all the oldies have done, but you should not believe everything until you have examined it for yourself all over again. So this is just a quick introduction to the issues that are there. I wanted to, so let me say where this places us phenomenologically. What are we supposed to do? What are we supposed to even imagine? And I want to argue, very briefly, that remember, our job is, many things are plausible. It's plausible that this whole notion of naturalness is just wrong. That in fact, the compositeness scale, if you believe in the compositeness paradigm, or the supersymmetry breaking scale, if you believe in supersymmetry, that this scale is incredibly big, and this notion of fine-tuning and no fine cancellations is a silly idea, that in fact there are plenty of fine cancellations, and that's just the way the world is. And this scale is so big that we'll never see it in the next generation. But our job is to, again, find the intersection, and maybe that's plausible to you. But our job is to look for what is both plausible, that gives us something to do experimentally, right? That we can actually probe and test. And so, I'm saying this sort of, life is going to be great tomorrow, and life is going to be dreadful forever, that these are two extremes, 0-1 thinking, and we have to rethink what is the middle ground, okay? And so let me first say the life is going to be great philosophy is here is energy, here's the standard model, very rich. We often say the joke in supersymmetry, but now a joke that people cry and drink over, is look, we've already discovered half the particles of the supersymmetric spectrum. So, the typical UV completions, the typical solution to the hierarchy problem, for every standard model particle you double the spectrum or even more, you have a very rich set of excitations of the standard model, superparameters, whatever it is. And of course, if this is the LHC reach, effective reach, then this is what you should have expected. If there was really naturalness, without any fine-tuning, this is what would happen. We would be seeing these excitations, presumably, and it's so rich that we would have seen it in one channel or another. It might have been a subtlety in this channel, but then in another channel. It's just got too many pieces in it. Okay. But I think there are loopholes in this thinking that go in various directions. The most obvious one that is still consistent with all these ideas of naturalness, etc., is what I would call sparseness. It's the sparseness of the spectrum. This is a very densely packed new spectrum, which probably says that we're not seeing this. But obviously, we are still consistent. Experiment is still consistent with a picture that looks like this. And then experiment. This is the LHC. Experiment is still consistent with not seeing this kind of stuff, but just seeing this, where there is really a big doubling of the spectrum, but only a few particles happen to be a little light. Just look at the real world spectrum. The weak scale is the scale of the standard model. But then we have these piddling things, neutrino, oh, but it's hard to see. Electron, well, it's not that hard to see, it's there, okay? We're all made out of it. So spectra don't always just, we're using these very crude estimates, but stuff can drift down. And maybe the spectrum looks like this, in which case, one or two particles, they could have evaded our searches, because there could be a subtlety in each of those channels that makes it that hard, or it could just be a little bit out of reach of what the 7TeV, 8TeV LHC has done. So this is possible. But wait a second, is this consistent with naturalness? Don't we need all of this in order to solve the hierarchy problem? But actually that's not true, because you see, this is the dominant contribution to the expectation that lambda conc should be 500 GeV. It's this guy. So if the particles that are relevant to this calculation, the new physics that's relevant to this calculation, if you like, the composites, the scale that goes in here, is really not the mass here, but the mass of these guys, then we'd actually be okay. Because the other contributions to the Higgs self-energy are weaker. Okay, so they're more tolerant of raising the masses of other excitations. So it is in fact possible that that the spectrum looks a little bit qualitatively like this, and that one might shoot for only those composites that are relevant to the top, the biggest self-energy correction, the top quadratic divergence. Particles that are relevant to the top quadratic divergence are called top particles. There's a beautiful example, completely worked out, which in supersymmetry, if you think of these as superpartners and these as stops and spottoms, then these are the top partners. The superpartners at the top are the top partners. They are the ones that are relevant to this quadratic divergence. They are the ones that show up in that place. Their mass is what sets that. And that is this kind of a spectrum where it's spread out, where the top superpartners are lighter, is called natural SUSY. And the job of the LHC cannot just say, I'm depressed and I'm stopping. It has to say, I've looked everywhere, under all possible circumstances, under all possible ways that naturalness itself is the theory now. Okay? I don't know which natural theory, Technicolor, composite Higgs, supersymmetry, experiment, I don't know. But the LHC's job is it has the energy reach, in principle, to say that the world is not natural to 1%, say. And there must be 1% fine-tuning somewhere. And that is an incredible piece of information, if it could provide it. But it has to be pretty complete in covering all bases. Which means that the search for top partners has become urgent. Stops are a beautiful example of top partners. Again, my paper on the subject is not the first paper on the subject that was invented long ago, but all the references are there. And my philosophy of relating it to this, you can read about there. So this is a good introduction to it. I believe Matt Strasser up there has done some, having heard his talk on it, has done some great work on the pheno side of how LHC searches constrain this a fairly recent state of the game. So let's also look at that. But what other kinds of top partners could there be? Is it only supersymmetry? No, I've just been spending all this time talking about composite Higgs. So there could be top partners which are not stops. They might have the same, they might look like excited tops. Okay, fruits of line tops. What other kinds are there? Have we categorized the different types of top partners that might exist? This is an important task. Some of us are still involved in trying to characterize what's going on. But the job of the LHC, a very complete job in some sense, and still incredibly challenging, is track down all incarnations of top partners and just show whether they're there or they're not. Okay. So this is a case where a sparse spectrum, meaning only a small number of particles within reach, is still consistent with the ideas of naturalness and all the grand ideas, but it is, all the true grandeur is delayed. Only the particles needed are showing up. Okay, I'm just seeing the problem. Of course, another possibility is that this is the same spectrum. It's the same spectrum, but these are what I'll call incidentally like. I find this even more plausible. These are incidentally like particles, meaning there's a rich new spectrum. The central players are out here. So in fact, there is fine-tuning. The fine-tuning is whatever, 1%, 0.1%, whatever it is. Which would then be a mystery. Why are we so unlucky? We're so unlucky all the time, and then we do particle physics and we still get unlucky, right? So why is that? But we're lucky enough that some random particle shows up light enough in the spectrum, just like the electron in real life, and hence we can see it. Okay, so that's another possibility. But if and you might say that's a very rosy story because you're telling me that there's stuff to see. But then why should there be fine tuning? What is it that's undercutting the perfectly reasonable statement that if you take 5 numbers of order 1, which are chosen out of a random number generator, that the sum of the 5 numbers is order 1, not 0.001. Incredible. You don't gamble like that. That's what's incredible. So why would the theory be sparse and yet unnatural is a remaining question. That's a story that I would call meso-tuning. Meaning, how much should you agonize about coincidences of 1%? Is it worth doing? in that sense, there's a sense in which the hierarchy problem, maybe you should treat it the way you do relationships. There's sort of, it's roughly good, it's roughly bad, but you don't keep score. Otherwise, everything goes down, right? So, maybe we shouldn't be agonizing about mesotuning. The reason we agonize about it is because the LHC is a very finite machine. It's not your dream machine. It seems to be just enough to cover the perfectly natural cases. And yet, if things were a little bit unnatural, so philosophically, you might say, look, I'm not going to sweat about 1% fine-tuning. That's just silly. But unfortunately, the LHC cares. Okay, so then you're forced to become a philosopher about small things. But this kind of spectrum is what I call mesotuning. And one would like to understand if there's any reason why the principles that they're giving here should not work perfectly. I mean, to order 1 with very little fine-tuning. Why should there be any mesotuning at all? Of course, it could just be incredibly bad luck, but that just doesn't. We would not put high probability on that. The other possibility is the ideas we've been talking about up till now are missing one important element. Okay, and indeed, as I said in the first lecture, soon after the acceleration of the universe was discovered in the late 90s, which can be fit in general relativity by a cosmological constant. The resemblance of the cosmological constant being small to the weak scale being small, field theoretically, made people take ideas that had been percolating for the cosmological constant being small, fine-tuning problem, and apply those philosophies to particle physics. And the result was applying, and those ideas were the ideas of the anthropic principle. And the idea was this, that there could be another way, so I'll just sketch it, and then I just want to make a statement that it's there. I was hoping to have a little more time to point out the subtleties in it. But the statement is that I didn't start there's nothing I said in these lectures which I have not tried to use twice, even though they seem like crazy. Let me come back to our friend the aliens, okay? So indeed, they have some version of the standard model which looks a little different from ours, have massively different consequences as we saw, but fine, the standard model has its parameters ways. So the idea is that in fact there really are many universes. Okay, so here's time, here's space. This is space-time, and there's some quantum gravity theory that rules over everything. But then it delegates to more small-scale counts and views, things like that. Quantum gravity has effectively got phases, different phases of quantum gravity, just like ice and water and all of those things. There are different possible phases that it can have. Or the usual word that we use is that it has different possible vacuum. Okay? And indeed we're used to this, where even the standard model has different phases. Earth has very different conditions from outer space and so on. And so somehow, the analog that's closest to the thing I'm going to draw is very much like domain walls in a ferromagnet. Again, there are all spins up, all spins down, and then there can be domain walls that separate them. This looks equivalent to this. Life here looks very similar to this. But in fact, there can be domains of inequivalent vacuum. That's the new concept. Even in condensed matter kind of situations, you can have situations where there are domains where the same Hamiltonian has different possible ground states, but the different ground states are not symmetry transforms of each other in the dumb way that this picture is. So that life for a little ant living in this domain looks very different from life for an ant living in this domain. It's not equivalent. That's what I mean by this. And Indeed, the one quantum gravity that we have any control over, namely string theory, indeed seems to, within anybody's ability to tell, have precisely these kind of many possible vacua, many possible phases that it could be in. Many, many, many possible ones. And so it's given rise to the picture of what I'll call a multiverse. It's called by various names, landscape, multiverse, where space-time is sort of carved up into domains. And things that we call the standard model are merely the effective field theory expanded around the basic ground state or vacuum that is the solution, the approximate solution to quantum gravity in this region. And the standard model are the small fluctuations around that particular vacuum. But then this could be standard model prime, this could be, not a standard model at all, and, whatever. There could be all sorts of things lurking here. Our aliens are from here, we are from here, okay, so they've just wandered over checking us out. That's it. Okay. That's the picture. And now we have a new degree of freedom in the discussion of this question that we asked earlier, which is in the standard model structure begs us to ask the question why the weak scale is so small. And we have been looking for a dynamical reason for why it's small. But the anthropic principle says, thank God it's small, because if it wasn't small, atoms, all the things were made out of nuclei, blah blah blah. If I just keep, this is an exercise where you keep the standard model fixed, you take this one parameter and you vary it, keeping everything else fixed. This is the only dimensional parameter in the standard model, and you move it in the Lagrange. You move it closer to the Planck scale, and you see what would life be like in that universe. Maybe that's this guy here, okay, where V is closer to the Planck scale. So V aboard the Planck scale. Here, V is much less than the Planck scale. And so in this universe, atoms are much heavier, etc., etc. And if you put even a few atoms together, you form a black hole. So it's not as livable a place. Okay? When we have this property, our weak scale being small, which sets the masses of all other things, we find that we can make a whole Earth, and it's not a black hole. We can make a whole galaxy for that matter, and it's not a black hole. So, I'm just giving the shorthand of it. The idea is that maybe we need it. We need this hierarchy that we see to be here to ask, to even be here to ask this question. What the hell is going on? So the idea is that there's a kind of anthropic selection, which is that this is not very likely. The standard model is in fact the correct theory. There's no Technicolor, there's no Susie, there's no nothing. And there's just, or if you want, another way of saying there's no compositeness. It's to merely say the compositeness scale is the Planck scale, and there's incredible fine-tuning. And so this is a very unlikely phase in this whole thing. This is a very rare, exceptional thing in the space that we're talking about. This is much more typical. But this is the only place that there's a person here to ask the question that we're asking. Okay. So that seems to undercut the mechanistic view that we've been trying to say, that look, this is such a striking fact, and that if you don't believe in fine cancellations, then I really expect some new physics to show up very soon. This seems to undercut it. And since I have -4 minutes, I'll just say in one line, the thing that I wanted to go out with a little bit of detail. The field has gone into those who say, like, that must be what's going on. Okay, that's it. It's all over. Because if this is true, and we can't get out over here to check out the truth of it, this is the entire universe that we inhabit, that if this is somehow the picture in any way, philosophically or truly this is out there, there's no way there may not be a mechanism inside this world that explains why this is there. In fact, it's such a rare event in the parameter space. You're throwing darts at this board. Every time you land here, you're okay. This is dynamics. You land here, you're dead. You land here, you're dead. You land here, you're dead. And so you live here, which in part means that the only livable place is things with a lot of fine tuning. So that picture has led some people to think, okay, that's the rules, and then they try to see if there's any predictive value to those rules, even though a priori it looks very hard, but then they're also quite ingenious. And the other part is people who say, look, I hate that. That would be so terrible that I blame you for telling me the story. I've seen exactly that happen, but I didn't tell the story. I didn't invent any of these ideas. But I have been in the room as somebody who's trying to say, well, maybe this is what's going on, has been like, how? and that's how people protect their self-interest, right? Very good. Now, I just want to leave you with the possibility that this, I think, I subscribe to the picture that this is very, very plausibly a way of thinking that you cannot forget once you have seen it and appreciate that it does make sense, it's not crazy. This is something you cannot forget. But it doesn't have to completely undercut this. Instead, and that was what I was going through a little bit, but I think there's no point in going in detail. I leave it to you to exercise, examine it. These two can both coexist. The probabilities for where you are and what kind of world you have, one with a mechanism for this or one where it's pure chance, they may actually come together so that there's a little of both kinds of pressure acting. Just like in statistical mechanics, you can have energy considerations and entropy considerations, they can balance in some way. The same thing is likely what's going on in the real world, and it is plausible that it results in something which is solving the lion's share. Most of the hierarchy problem is being solved, and yet not perfectly. That these anthropic considerations are undercutting in a certain way. Now, I had an example which was something that showed how that can happen, given the technology that we already developed. But I'm going to stop and leave it at that. But this is something you cannot forget because, again, your career depends on how you come down on it. You'd like to not have a belief, but what are you going to do? Okay, let's stop it.
Lectures, they were really
Bizarre.
the best. So, finish.
Thank you.
Let's thank you.